All right, so we talked about the ionization energy, or the first ionization energy, how much energy it requires to remove one electron. But what about successive ionization energies, right? How much energy does it take to remove 1, 2, 3, 4, 5 electrons, and so on and so forth? And that depends on what kind of electrons you're removing. So valence electrons are going to be relatively easy to remove because they've got a lot of core shielding electrons, so they don't feel as much of an effective nuclear charge. Whereas core electrons are going to be much more difficult to remove. So for example, like group 1 elements, something like lithium, sodium, potassium, right? We know that they want to have that charge of potassium plus, Na plus, lithium plus, potassium plus, right? We know that they essentially want to lose one electron, and that's because they have one valence electron. So if you were to take a look at their ionization energies, right? You take a look at IE1, right? How much energy it takes to remove the first electron, the second electron, the third electron. What you would see is that the first ionization energy is relatively small because it's easy to remove valence electrons, or at least relatively easy to remove valence electrons. And then after that, if you try to remove core electrons from that, there'll be a big gap, and it'll be quite hard, right? So it'll take much more energy to remove these core electrons. So let's think about another element and try to kind of make a prediction about which electrons are going to be easy to remove, which electrons are going to be hard to remove. So for example, we've got boron. If you think about boron, it's got 3 valence electrons. And if we think about its kind of Bohr model diagram, we have this n equals 1 and then n equals 2. So it's got these 2 core electrons, and then it's got these 3 valence electrons. And these valence electrons, since they're furthest away from the nucleus, they should be the easiest to remove. And so what we would predict would occur is we've got all of our ionization energies here. And we would predict that the first 3 electrons are relatively easy to remove. That doesn't necessarily mean that they're easy to remove. It's just relative to that 4th electron, right? Once we try to remove that 4th electron, now we're trying to remove one of these core electrons, and that should be extremely difficult to do. So we should see a big gap, right? It should be much harder to remove these electrons, right? So we should see a big energy gap because we're now trying to remove core electrons. And so that's our prediction. Let's go ahead and take a look at some data. And check it out, right? So boron is right here. We can see that its first 3 ionization energies, 800, 2500, and then about 3700, right? Those are big numbers, but then you look at that 4th ionization energy, and it's 25,000, right? So almost 8, 9 times the amount of energy it takes to remove that 3rd electron. And you can see it's all based on the number of valence electrons. Lithium only has 1 valence electron, so its first valence electron is easy to remove. Its second one, now a core electron, is much more difficult. And that trend goes all throughout here, right? Oxygen, 6 valence electrons, 6 electrons, relatively easy to remove. That 7th electron, now a core electron, much more difficult to remove. Right, so we kind of did the science thing, right? We used the periodic table / our understanding of quantum mechanics to make a prediction. Right, we predicted that the first 3 ionization energies of boron would be relatively small and the 4th would be large. And then after that, we tested our prediction. I'm going to put tested in quotes. Right, by testing, I mean, we looked at an image, we Googled it. In real life, you actually do experiments, but that's what it's all about. You have some kind of model of the way you think that the world works, and then you go out and you do experiments and you see if your model works. If it works, then you have more support for your model. If it doesn't work, then you have to somehow modify your model to fit what's going on in real life. And then, of course, hopefully in real life, your predictions are useful in some fashion.